Hello friends, today's our lecture is on Boolean Algebra and Digital Logic. Here we will learn everything of Boolean Algebra related topic. Now, before starting, it's my request to subscribe our channel and press the bell button for future links. Future all the videos you will able to get from there. Now we will start today the Boolean algebra. It's very basic thing for our digital electronics. And those who don't know Boolean algebra can't able to get this. Let's start the Boolean algebra. Before that, please subscribe our channel. Now, first of all, Boolean algebra's application area we will discuss. The application of Boolean algebra is used to perform logical operations in digital computer. Digital computer, true represented by high volt, that is 1, and the false represented by low volt, that is 0. This logic operator must be controlled by the AND conjunction operation or disjunction and not, that is the negation or complement operation. These are the very fundamental logic operators. Now, AND operators is showing that it is the dot form, that is x dot y. If the inputs are 0, 0 in x and y, then it will give us 0. 0, 1 also 0. 1, 0 also 0. In case of OR operator, just it will represent plus, that is 0, 0, 0, else all 1. In case of the NOT operator, it performs the logic negation denoted by negation of bar, that is 0 by 1, 1 by 0. This means the complement of x. This is operated by single variable. Now we have to know the truth table. What is truth table? Truth table is a table that contains all possible values of logical variables and statement in a Boolean expression. Now here the number of possibilities must be 2 to the power of n. N is the number of variable in the Boolean expression. Now the truth table show you what way to represent the detail. That means by using this table, the all logical variable statement of a Boolean expression must be show you all possible combinations. Let's start with the tautology and fallacy. What is tautology? Which must be always true, which is negation is not possible, complements is not possible, that is tautology. And the output of Boolean expression always false is known as fallacy. We are representing here, that is 0, 1 equal to 1, 1, 0 equal to 1. If always 1 is showing, that is our tautology. And just negation of that, that is nothing but fallacy. From this truth table, we can able to get that. Now the Boolean algebra, let's start. The Boolean algebra applied to the computer electronic circuits. These circuits perform Boolean operations, and this is called logic circuits or logic gates. Now, for this logic circuits and logic gates, this circuits represent always the Boolean operations. It is used by 3 logic gates, that is the digital electronics very basic things for any type of signaling and their outputs. Now here, if the 1 or 2 more signals has come as input and produce one output, the gate are digital circuits because there are 2 things we are getting, either 1 or 0, that is high voltage or low voltage. Basic Our operations we already discussed, that is and, or, and not get. This and, or, and not get, we have to discuss it right now. How can we explain it? Or get, and not get. Let's start the discussion about and, or, and not get. And get. The AND gate is an electronic circuit that gives us high output only when both the inputs are high. Here we are representing the gate design along with the truth table. I think it is visualized right now. AND gate take two or more input signal and produced only one output signal. Now, for NAND gate, the design is showing here two input NAND AND gate. This AND gate, next OR gate is coming. Here the OR gate showing you, that is, it gives you the output only any one of or both inputs give you the one. The OR gates take two or more input signal and produce only one output. The gate design and truth table is given here. Here we can see that 0, 0 representing 0, 0, 1, 1, 1, 0, 1 and 1, 1 is also 1. Next come to the NOT gate. Very basic gates, NOT gates, one input and one output. Output is the complement of the input. It is called inverter also. This is the electronic circuits give high input when the input is low. High input, low output, and high output, low input. This is the basic concept because it is called also inverter. So the NOT gate is an electronic circuit, gives us high output 1 when the input is low, that is 0. Now, after doing the NOT gate, we will start our discussion about the basic things of another, that is nothing but the Boolean laws. These Boolean laws are very important for us to discuss right now. Based on this three logic, our all Boolean laws will be there. Now, before starting these Boolean laws, we should know our duality. Let's start with the duality. Principle of duality tells us in Boolean algebra, the duality principle can be obtained by interchanging and not operation, by replacing 0 by 1 and 1 by 0 to compare the identities on the left side with the identities on the right side. Let's take one example. A plus 1 gives us 1. That is, it is right now 0 is represented by 1, 1 by 0. And A dot 0 is always gives us 0. That is called our principle of duality. That is, principle of duality is telling what? We can able to get that just interchange of 0 by 1 and 1 by 0. Now comes to the basic theorems of Boolean algebra. Now the properties 1 is telling 0 plus 1 equal to a. 0 dot a equal to 0. These are the properties of 0. And the properties of 1 is telling 1 plus a equal to 1. A dot 1 equal to a. These are the properties of 1. In based of this two, zeros properties and ones properties, our all Boolean expressions and all Boolean theorems or our expressions are there. Based on this two, everything are there. Now let's start the next one. First one, that is the commutative law, is telling us a plus b equal to b plus a and a dot b equal to b dot a. This is commutative law. Next one, associative law, is telling a plus b plus c equal to a plus b plus c. A dot b into c is called a into b dot c. This is the associative law. Next one, the distributive law, is telling a dot b plus c equal to a dot b plus a dot c. And a plus bc is known as a plus b dot a plus c. And another, a plus a complement into b is known as a plus b. Next, the idempotent or identity law is telling a plus a equal to a dot a equal to a. Now the next one, complementary law, x plus x complement gives us 1, x dot x complement gives us 0, and the evolution x double double complement, that is complement of complement, gives us always x. And the De Morgan's, very known De Morgan's theorem, a plus b whole complement equal to a complement dot b complement. A dot b whole complement gives us a complement plus b complement. Now the Boolean expression can be expressed by two ways, that is either SOP or POS, that is sum of product or product of sum. We can take two example. AB plus AC is known as SOP, whereas A plus B dot A plus C is known as POS. These are the example of SOP and POS, that is sum of product. In case of AB, that is product summed by A plus AC. Now we should know the canonical form of Boolean expression also. The standard SOP and POS is either each of the term of the Boolean expression must contain all the literals with and without bar that has been used as Boolean expression. If the condition, that is above mentioned condition, is satisfied, then by Boolean expression, that is we expressed, is called canonical form of the Boolean algebra or Boolean expression. In Boolean expression, a b plus ac, the literal c is missing from the first term and b is missing from the second term. That is why AB plus AC is not at all a canonical form. That is, it is a SOP, so it is also canonical SOP. Now to convert into the canonical form, canonical SOP, what we have to do? AB plus AC, AB, C is missing, so C plus C complement, that is 1. We can multiply it here. And similar, AC, where B is missing, we are giving B plus B complement. Now, after distributive law, ABC plus ABC complement, ABC plus AB complement C. Now, ABC are common, so we are not taking it, will be 1, that is ABC plus ABC bar and this. Now, for POS canonical form, A plus B dot A plus C. Here also, what the missing? First one C is missing and second one B is missing. So we will give that there and we will produce A plus B plus C dot A plus B plus C complement plus A plus B complement C. Now we should know the mean term and max term of the Boolean expression. Individual term of canonical sum of product is called mean term and individual terms of the canonical product of sum POS is called max term. So, in other words, max term is the sum of all literals and mean terms is the product of all literals with and without bar. So, I'll again repeat, SOP is termed as mean term and POS as max term. Based on this mean term and max term for two variables, the deviation of Boolean function with their two tables is given here right now. Suppose x, y, two variable. So 0, 0, 0, 1, 1, 0, 1, 1. It will be indexed as 0, 1, 2, 3. First one, when x 0, y 0, that means m0 is x complement, y complement. The similar way for three variables also we can able to get. When x, y, z all are 0, it gives us mean term x complement, y complement, z complement. But in case of product of sum, we get max term. There we will get when x0, y0, z0, we will express it in this way, x plus y plus z. Now, for the next one, 0, 0, 1, that is z only 0. Similarly, we will get x bar, y bar, z, x, y bar, y, z bar. That means when the 1 is coming, that will be 1 represented and another will be complemented in case of mean term. And in case of max term, whatever the complement, that is one logic is coming, then we have to say this is our opposite sense, that will be 0 will be high logic. One solved program is given here right now. A complement BC plus A B complement C complement plus A B complement C plus A B C complement plus ABC. Now here from, by taking the first ones, that is A complement A, we will able to get A complement A, B, C. The first and second one, that is A and A complement, will be gone. This is our lecture. Now next day we will explain more with the K-map. Thank you and please subscribe our channel. Now before ending, one thing I have to tell you, in case of this, all the gates must be represented by some universal gates also. We will discuss it in our next